Swayam Prabha. Digital India. Educated India.
We have studied dynamics of a particle. For solving the dynamics problem, we used Newton's law. Particularly in solving the numerical problems, Newton's second law was used. In place of Newton's second law, we can also use D'Alembert's principle. D'Alembert's principle is not much different from Newton's law. It basically considers minus m into a equal to a force, that is called inertia force. Thus, a problem of dynamics can be converted into a problem of statics. But essentially, both the approaches are making use of the equation F is equal to mass times acceleration, where F is the resultant force, net resultant force acting on the body, and m is the mass, a is the acceleration. Now, here one point has to be noted, that the acceleration has to be measured from an inertial frame of reference. An inertial frame of reference will be moving with a constant velocity, including 0, it may be moving with a 0 velocity with respect to a primary inertial system. A primary inertial frame of reference is that frame of reference which is at rest. Now, so thus we see that D'Alembert's principle and Newton's second law essentially are the same. Now, today we discuss a different approach of solving the dynamics problem, that is work and energy. Now, you will see that this formulation is quite different, although it can be derived from Newton's second law. In work and energy, we will say not talk about the same type of things as we talk in Newton's second law. In Newton's second law, one requires acceleration. Here, another approach may be there, that you require only the measurement of velocities and force and distance. Then also the same type of solution can come. So, in case if you have to just find out the velocity after the application of force at some distance, then instead of going by Newton's second law, we can directly use work and energy. Newton's second law provides a differential equation, that is F is equal to m d square r by dt square. Here you will get a type of integral equation which can be solved in a different manner. Although Newton's second law and work and energy approach follow different procedure, they are basically derivable from each other. Now, I will explain the basic concepts. Newton's law for a particle moving relative to an inertial reference frame is given by F is equal to m d square r by dt square, which is equal to m dv by dt, where r is a displacement vector and v is the velocity vector. Here I am considering the mass of the particle to be constant. If we multiply each side of the equation by a vector dr as a dot product and integrate from r1 to r2 along the path of motion, the particle may be moving from r1 to r2. So, this is 1, 2. So, its position vector of 1 is r1, position vector of 2 is r2. We can integrate the dot product of f and dr from r1 to r2, which gives us r1 r2 f dot dr is equal to m r1 to r2 dv by dt dot dr. I have taken m outside the integral sign, considering mass to be constant. So, therefore, this has become m r1 r2 dv by dt dr by dt into dt is equal to m t1 to t2 dv by dt dot v, where dr by dt has been written as v. This is equal to half m t1 to t2 d by dt v dot v dt, where the product law of vector calculus has been used, that is d by dt v dot v is equal to v dot dv by dt plus v dot dv by dt. So, which gives you half m t1 to t2 d by dt v dot v dt. This expression becomes half m t1 to t2 d by dt v square dt. Now, see the dot product v dot v is a scalar, that is v square, which is the magnitude squared of velocity. So, this becomes half m t1 t2 d by dt v square dt is equal to half m v1 v2 d v square. That gives, here I have changed the limits of the integration because the variable dt has vanished from here. So, this becomes half m v2 square minus v1 square. Thus, the work done on the particle is equal to change in its kinetic energy. Therefore, this essentially has come from Newton's second law. Therefore, instead of Newton's second law, one can use this theorem that work done on the particle is equal to change in its kinetic energy. If you know the force acting on the particle and you know the displacement vector, then you can find out the work done. You can equate it to change in the kinetic energy, and thus you can find out the final velocity if you know the initial velocity. We have to see that is it possible as to find out instead of magnitude, we can also find out the components, various components of the velocity. If we write Newton's law in component form, then fxi plus fyj plus fzk is equal to m dvx by dt I plus m dvy by dt j plus m dvz by dt k. This Newton's law has been written in the component form. Fxi is therefore fxi is equal to m dvx by dt I. Thus, if we take the dot product of this equation with dxi plus dyj plus djk is equal to dr, if we take the dot product of the equation, not the dot product of f with dr, but dot product of fxi is equal to m dvx by dti with this dr, then we will be getting that x1 x2 fx dx will be equal to m dvx by dt into dx, which when it will be integrated, it will provide us m by 2 vx2 square minus vx1 square. Similarly, we can also get y1, y2, fy dy is equal to m by 2 vy2 square minus vy1 square. Similarly, z1, z2, fz dz is equal to m by 2 vz2 square minus vz1 square. Thus, the Newton's law is also valid in the component form. Thus, the work done on a particle in any directions equals the change in kinetic energy associated with the component of velocity in that direction. This is very important because we can find out the velocity components by using the work and kinetic energy equation. Now, one example is provided. If a car and a truck are moving with the same kinetic energy and the same braking force is applied to them, which one will cover more distance without stopping, car or truck? In this case, if we want to apply Newton's law, we have to do many arithmetic computations. We have to find out the acceleration of the truck and cars, and after that we have to apply equation of motion in order to find out the result. Here in this case, we can quickly find out the answer by applying the work kinetic energy theorem. Since both the vehicles are having same kinetic energy, change in kinetic energy will be same. Thus, the work done by the braking force will be same. Given that braking force on the two vehicles is same, the distance covered by them is same. So, here you get a simple relation that F is the braking force, F into S is equal to change in kinetic energy, delta Ke. Since change in the kinetic energy is same, therefore braking force comes out to be same. This shows that how efficient it will be applied to work energy theorem in many cases. Now we will discuss something more about these things, but let us go to the another definition. We define power. Power is the time rate of doing work. Accordingly, the power P developed by a force F which does an amount of work W is P is equal to dW by dt. That means this is equal to F dr by dt, that is equal to F dot V. Here in this case we have obtained this expression in the following manner. P is equal to dW by dt. dW by dt is dF dot dr by dt. We take F as a constant which does not depend on time, take it out, then you get F dot dr by dt. In case F is dependent on time, then this can be written as F dot dr by dt plus dF by dt dot dr. In this expression we get additional term F dot dr by dt surely can be written as F dot V. However, we will get extra term, that is dF by dt dot dr. This, so if F is changing with time, then dF by dt must also be evaluated and multiplied with dr. However, if we consider the dr to be very small, then in that case this term becomes insignificant. We give one example where the force is changing with time or distance. For example, consider a spring. Now, a particle attached with a spring is moved, then the spring force is dependent on the extension of the spring. In this case, P will be equal to F times dot V plus dF by dt dot dr, which for one dimensional case we can write as dx. Now this can be written as F dot V plus dF by dt. dF by dt can be written as dF by dx. This can be written as dx by dt dx, which dF F is equal to minus kx. Therefore, dF by dx is equal to minus k. Therefore, the second term can be written as minus k dx by dt, that is minus kV dx. So, therefore, the expression for power is in this case minus force into velocity minus kx into V plus minus kV into dx at any. Dx is infinitesimally small. In that case, the power will still be minus kx v. However, if the force has some singularity, in that case this term may be significant. Concept of power is found very useful in certain context. Now suppose a man rises walking on the top of a hill and another man goes riding on a motorbike. Both have done the same amount of work, but the second man used more power because he would have done the same amount of work faster. So this is this one. Now we discuss about the conservative force field. Force fields whose work is independent of the path are called conservative force fields. Force field, we understand the force field, forces, but what is force field? Force can be expressed as a function of x, y and z and time also. Therefore, so when we express force as a function of x, y, z, then it becomes a vector field. Force is a vector, so this is a vector field. Force field in this, so there can be different type of force fields. A field in which work is independent of the path are called conservative force fields. One example is gravitational field. Suppose the particle is moving from 1 to 2 under the influence of gravity, like this. In that case, work done by the force is W is equal to 1 to 2 F dot dr. R is the position vector of particle at any instant. R keeps on changing as the particle is moving towards paths, like that. Dr is the distance between two position vectors, like at this instant this is dr, and provided the difference is very small, therefore it is indicated by dr. Work done by the force is W is equal to 1 to 2 F dot dr, which is 1 to 2 minus mgj, because the force is always constant and that is directed downwards in the y direction. Therefore, it is minus mgj dot dr. Dr can be written as dxi plus dyj plus dzk. Dot product of j and I 0, dot product of I and k 0, therefore we are left with minus mg dy, because j dot is 1, which gives us minus mg y2 minus y1, that is equal to mg y1 minus y2. Thus the work done is dependent on the end coordinates y1 and y2 only. It is not dependent on the path of motion. The particle can adopt any path. It could have gone like this to the same point, it could have gone like this, or it could have gone in a straight line. The work done will be same, it is dependent on the end coordinates y1 and y2. Therefore, the gravitational field will be called a conservative force field. Similarly, if the particle goes from 1 to 2, the work done is mg y1 minus y2. Work done by the gravity on the particle is mg y minus y2. If the particle would have gone from 2 to 1, the work done by the gravity on the particle will be mg y2 minus y1. Add both the works, you get 0. So, in the conservative force field, if a particle undergoes a cyclic motion like this, completes the cycle, comes back to the original position, the net work is 0, which is not the case in non-conservative force field. So, in general, for a conservative force field, Fxyz along a path between positions 1 and 2, the work is W1 to 2 F dot dr, that is equal to U1 xyz minus U2 xyz, where U is a function of position of the endpoints and is called the potential energy function. Like in the previous case, you got work done between 1 and 2. It is mg y1 minus y2. So, mg y1 can be written as the potential energy U1. mg y2 is the potential energy U2. U1 and U2 are functions of xyz. U1 is equal to y1 is a function of xyz in which other coefficients are 0. So, it is U is a function of position of the endpoints and is called the potential energy function. Now, we note that minus 1 to 2 F dot dr is equal to U2 xyz minus U1 xyz, which is delta U. Note that potential energy function depends on the reference xyz used or the datum used. However, we will be concerned only with the change in potential energy delta U, because work done between 2 points will always be the difference of the two potential energies, and therefore it is independent of the datum used. So, any datum can be used for defining the zero potential energy. In kinetic energy calculation, the zero velocity use zero kinetic energy, but this is not the case with the potential energy. In potential energy, you can take any datum and you can find out delta U, which will be independent of the datum used. Change in potential energy delta U of a force field is the negative of the work done by the force field on a particle in going from position 1 to position 2 along any path. Therefore, force field, when the force field does some positive work, then the potential energy increases. If the force field does the negative work, then the potential energy decreases. Delta U, change in potential energy delta U, work done, negative work done. So, work done by the force field work done by the force field is, if you negative of the work done by the force field is equal to change in potential energy. For any closed path, clearly the work done by a conservative force field F is integral F dot dr equal to 0. Now, for an infinitesimal path difference dr is starting from 1, F dot dr is equal to minus du, that is fx dx plus fy dy plus fz dz is equal to minus delta u by del x dx plus delta u by del y dy plus del u by del z dz. Thus, fx is equal to minus del u by del x, fy is equal to minus del u by del y, fz is equal to minus del u by del z, or f is equal to minus gradient of u, where u is a scalar field and this is indicated by minus delta u. Gradient of gradient is defined as, this is a gradient operator which is defined by del by del xi plus del y by del yj plus del by del zk. This is in the Cartesian coordinate system. In the same way, it can be defined in the rectangular polar coordinate or spherical coordinate system. So, if you have got a conservative force field, it can be expressed as a gradient of some potential energy function. Thus, a conservative force field must be a function of position and expressed as the gradient of a scalar function. If a force field is a function of position and the gradient of a scalar field, it must then be a conservative force field. Now, in some books, it will be shown that for a conservative force field, curl F is equal to 0, that is curl of the force field is equal to 0 for a conservative force field. Curl F of a vector is basically del cross F, where the del operator has been defined here. Now, this can be written as I j k del by del x del by del y del by del z minus del u by del x minus del u by del y minus del u by del z, because a conservative force has got these components. Therefore, this becomes I minus del square u del y del z plus del square u del z by del y. But for continuous u, this term will become 0. Similarly, the other terms will also come out to be 0, minus j minus del square u del x del z plus del square u del x del z plus k minus del square u del x del y plus del square u del x del y is equal to 0. Thus, you can judge whether a force field is conservative or not by finding out the curl of the force. Although this is true for this function which is not having the singularity in certain cases, like if you have fx is equal to y divided by x square plus y square, fy is equal to minus x divided by x square plus y square, fz is equal to 0. This force field provides curl F equal to 0. However, this force field is not conservative. Thus, curl F is equal to 0 can be called a necessary condition but not a sufficient condition. Sufficient condition is from the basic definition. A force field whose work is independent of the path is called conservative force field. Now, what are the examples of the conservative force fields? Linear force. If the force is given by F is equal to AXI plus BYJ plus CZK, then it can be expressed as the gradient of U is equal to AX square by 2 plus BY square by 2 plus CZ square by 2, where A, B and C are constant. If you take the gradient of U, this becomes AXI plus BYJ plus CZK. One example is a spring force. If we put B is equal to 0, C is equal to 0 and A is equal to minus K, we get a force field that is F is equal to minus KXI. The corresponding potential energy from this is U is equal to Kx square by 2. So, the spring force is a conservative force. Now, we discuss the conservation of mechanical energy which is valid for a conservative force field. We know from the basic concepts developed in the beginning that R1 R2 F dot dr is equal to half m V2 square minus half m V1 square. This has directly come from the Newton's second law. Using the definition of potential energy, that is V R F dot dr is equal to actually negative of the change in the F is the work done on the particle by the field, and it has the tendency to decrease the potential energy. The force field is trying to decrease the potential energy. So, therefore, R1 to R2 F dot dr minus U2 minus U1. If the particle works against the applied that force field, if you could raise that particle in the gravitational field, then the potential energy of the particle will increase. But if the particle is allowed to freely fall, then the potential energy will decrease. force field is doing some work on the particle, and therefore the particle's potential energy is decreasing. It will try to make the potential energy minimum. So therefore, if you don't constrain the motion, the particle will keep on moving. If you drop one object from the 6th floor of a building, it will reach the ground floor. If there was a pit at the ground, then the particle would have gone in the pit. If the pit was even deeper, it would have gone even more deep. So it is like that. So the force field tries to minimize the potential energy. Now, so therefore this point is important, that R1, R2, F dot dr is basically U1 minus U2, not U2 minus U1. Using the definition of potential energy, U1 minus U2 is equal to half m V2 square minus half m V1 square. We can take this to this side and we say U1 plus half mv1 square is equal to U2 plus half mv2 square. Thus, the sum of the potential energy and the kinetic energy for a particle remains constant at all times during the motion of the particle, provided the force field is conservative. Thus, in a gravitational field, that kinetic energy plus potential energy of a particle will remain constant. If you throw a projectile, then during the motion of the projectile, this kinetic energy plus potential energy will remain conserved. It will remain same throughout its flight. Therefore, this conservation principle can be applied at many places. However, if there are non-conservative forces such as friction force, which of course is non-conservative because it depends on the path of motion, in that case conservation of energy cannot be employed. However, this basic thing, that R1 R2 F dot dr is equal to half mv2 square minus half mv1 square holds good because it directly comes from Newton's second law. Condition is that you must identify proper F. If you have, it is not only what you have applied, but also friction forces. All external forces have to be included in this. Now, we have learned that in this case, F dr is equal to this half m v2 square minus v1 square is a very basic equation. Let us see whether what velocity should be taken if I am doing the work on a train. A train is moving with a constant velocity. You have a particle and displaced by some amount dr or some amount r. There has been done some work on this thing. Particle has displaced by an amount of r in a relative frame of reference, that means in the frame of reference of the train. In the absolute frame, for an observer who is standing outside, the particle has displaced even a greater distance. Similarly, the velocities. So the question is that in this case, the velocity, which velocity should be taken? Whether the velocity relative to the frame of reference or the absolute velocity of the particle in calculating the kinetic energy. Let us go to basics for understanding this. F dot dr is equal to m, this here that force m dv by dt. Here this v is the absolute velocity and this dv by dt is the absolute acceleration. That means as observed by a man standing in the inertial frame of reference, which is ground in this case, and this is dr. This can be written as m d vt, that velocity of the train, plus v relative, v rel, by dt dot dr. Now let us consider that we are taking this r is relative r. So F dot dr is the work done in the relative frame of reference. Work done will depend on the reference frame chosen. If you have applied a force F on the particle, the work seen by the outside observer may be more, but in this case it is F dot dr in the relative frame. So m dot d m dvt plus v rel by dt. If vt is constant, then in that case this equation just simplifies to m dv rel by dt into dr, which can be written as m v rel dr by dt dot dr by dt dr. dr by dt is again v rel, which will give you half m v rel square minus v rel 1 v rel 1 square. This is v rel 2 square, this is minus 1. Therefore, this relation, that work kinetic energy theorem, can be applied in the inertial frame of reference, that means which is moving at a constant velocity, provided you take the work done in the relative reference frame, that means force multiplied by the displacement in the relative frame, and is equal to change in kinetic energy in the relative frame. In this case, v2 and v1 should be the relative velocity in the frame, not the absolute velocity. What happens if the frame is non-inertial? That means dvt by dt is not 0. Train is having some acceleration, and that is indicated by at, acceleration of the train. In that case, it becomes m f dot dr is equal to m d va vt plus v rel by dt dot dr, which will be equal to m at plus m dv rel by dt dot dr. I can take this mat to this side and can write that f minus mat dot dr is equal to m dv by dt dot dr, which gives you, this is half m v 2 square minus v 1 square. Thus, the work energy theorem in the case of non-inertial frame can be implied provided you replace the force by effective force, that is F minus m at, where at is the acceleration of the frame, and then in this case it will be v relative square minus v 1 square. These are the relative velocities. Now, let us discuss some interesting things about of the energy approach. We have discussed the work energy theorem, that work done, if you do a work on this one, that is change in the energy. Now, we also have a principle for conservative system, that is principle of minimum potential energy in statics. When a conservative force field is applied, the potential energy of the system tries to be minimum. Now, if you take a spring and apply a force F, in this case the potential, if you give a displacement x, potential energy as a function of x has been can be written as this: U is equal to total potential energy, if I indicate it by big pi. So, big pi is equal to half kx square, strain energy of the spring, minus Fx. Remember, the potential associated with the force has been written as minus Fx, because if you take the negative gradient of minus Fx, you get equal to plus F. So, here many times students make confused, they may put half kx square minus plus Fx. Similarly, sometimes the students may put half Fx, considering that the force is gradually applied and therefore the work done is equal to half Fx. Remember that this is not a work done, rather it can be called a potential. So, this is potential. So, this is, so pi is, now the value of x which minimizes the potential energy will be the solution of the problem. For that, the necessary condition is that d tau by dx is equal to 0. Thus, kx minus f is equal to 0, and we get kx is equal to f. If the potential energy gets minimized, then it is a stable equilibrium situation. In this case, we can see that d square pi by dx square is equal to k. As k is positive, so this is minimization problem, this is a minima, and therefore x is equal to f by k provides the stable equilibrium of the spring force system. If the same problem is done by the work energy concept, then it can be done in this way. If the force is equal to, in this case force is F. However, this F is applied very gradually. Spring force is linear, therefore the force is also linear. At each and every stage, the applied force and the stretching force is balanced. So it is a quasi-static situation. No dynamic effects are there, and therefore it is linear. So in this case, the work done will be equal to half Fx. This work done on the spring is stored as the potential energy of the spring. So the potential energy of the spring increases because external force is doing a work against the conservative force field, that is in the opposite direction, minus kx. So this half Fx will be half kx square, and which gives us the solution as x is equal to F by k. So we get the same thing by the work energy theorem. Now similar to the case of statics, we have the principle in the dynamics too, that is called principle of least action. Action is along the particle's trajectory is defined as kinetic energy minus potential energy, Ke minus Pe, and so this is instantaneous action, the total value of the action across the trajectory from T1 to T2, time T1 to T2 is Ke minus Pe dt. One can write it same as Ke average minus Pe average, where the average is appropriately defined. Average is not just the arithmetic average, it is by the integration. Now if the particle follows that path which minimizes its action. So this is the thing. So this theorem can be used. Therefore, if a particle is moving from here to here, there can be various paths. But out of all paths, the particle will follow that path which provides the minimum action. We can show from the principle of least action that a free particle that starts from one position at time t1 and arrives at a different position moves along a straight line here. So this is the particle position, this is time, and this is particles, that x. Now how to find out the minimum path? This requires some advanced study. It is not possible to find out this by means of by taking so infinite number of paths and evaluating that. Even the fastest computer will not be able to do. So to study these type of things, one has to study calculus of variation. However, that we will not be discussing this point here.